Romano, see you're doing more physics.
Hi, I'd like to go over a question with you today on Bernoulli's principle. If this problem really scares you, here's the bottom line. And if you can walk away with this much, I think I'll be happy. I want you to never forget that along a streamline, pressure and velocity vary indirectly. So the pressure increases, the velocity will decrease. All right, let's do a mathematical problem.
Okay, Dr.
This is
Romano.
going to involve an airplane. A wing of an airplane has an area of 60 meters squared, has air passing over the top and the bottom surfaces at speeds of 320 and 290 meters per second. Find the lift force. And the density of air is given as 1.29 kilograms per cubic meter. I drew an airplane, and whenever there's a plane, the wing speed at the top and below is different to provide a lift force. Here it's 320 above the wing and 290 below the wing. You always have to have a difference of velocities. Now, essentially, this law looks confusing and it's scary. But like I said, pressure and velocity vary inversely is what it's telling you. Mathematically, we're going to see that the sum of the pressures, kinetic energy per unit volume, and potential energy per unit volume has the same value along a streamline. So let's draw our streamline from here to here. I'm going to first write P1 plus 1/2 rho, rho stands for the density, rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Before we do anything, we're comparing one point here and one point here. The height isn't going to change. We're going to assume that the flight is level, so the two heights go out. That's easy enough, so we're left with P1 plus 1/2 rho V1 squared. That's the kinetic energy per unit volume. Sort of looks like 1/2 mv squared. And the rho GH, of course, is the potential energy per unit volume. So I have P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Let's bring the P2 to the other side and bring the 1/2 rho V1 squared to the other side. P1 minus P2 is delta P equals 1/2. Notice I'm going to factor out 1/2 rho. So it's 1/2 rho times V2 squared minus V1 squared. Wasn't so bad. We know the density of the air. It's 1.229 kilograms per meter cubed. Don't forget, a fluid is a liquid or it could be a gas. Here the fluid is air. We know the velocity above the wing, the velocity below the wing, and we come up with 11,803.5 pascals. Notice the units of pascals is the SI unit of pressure. Now that we got the change in the pressure, what's the lift force? You should never forget pressure is force divided by area. We know the pressure, we know the area, and therefore we can get the lift force, which is 7.1 times 10 to the 5th newtons. And there you have it. That's the way you would mathematically do a problem using Bernoulli's law. But like I said, I think for an exam that's multiple choice, most likely you're going to have to understand the principle. As long as you can understand when the pressure is high, we're going to see the velocity is low. All right, I hope this gives you some idea of how to do some of these problems on fluid mechanics. You'll see more of them in the Physics Destroyer.
Thanks, Dr. Romano. I'm going to remember pressure high, velocity low.
Right. Good luck to you. Bye-bye.
I got it, Dr. Romano. Good day to you, sir.